Okay, this is a review for exam 1, physics 1102, exam 1 review. All right, check the date when it opens. It should be opening in a few days. You'll have one attempt. It'll be multiple choice with a number of problems, just concept questions and problems with that. All right, it will be timed. It'll be approximately 100 minutes to complete the test, so you should have plenty of time to do it. And it'll be on chapters 15 through 17. So I will be going through that and talk about the chapters, the question topics for the exam. So I've gone in all the details as far as the chapter lectures. We also have the first 2 labs are open and go from there. So, all right, so on the exam, all right, so section, so chapter 15, leave that up a minute. So on chapter 15, what we have, I have section 1, which is on first law of thermodynamics. I'm just going to put down that, and that's delta U is Q minus W, or again, that's the internal energy. Q is the heat added, and W is the work done by the system. And work done means it actually has to physically move something. So most of it, again, with gases, or again, we have the ideal gas law. It's PV equals nRT, and internal energy is given by 3/2 nRT. So the change in internal energy is with the temperature. And again, we're using always degrees Kelvin for these problems. So that's the first law there. That's the second law there. Different processes, again, for section 2, we have isothermal. I've gone through that. Isobaric processes, isovolumetric, and adiabatic process. So again, in the textbook on section 15.2, table 15.1 describes each of the processes quite well. And again, for all of this, for a PV curve, the work done is the area under this curve, so that's the work done is the area under the curve of this P versus V graph. Okay? So that's section 15.2. 15, we're not doing 15.3, 15.4, and 5, again, on efficiency. So I'll leave this up for a minute. So again, check the expressions for each of these, because I may just refer to an adiabatic process. What does it mean? What do each of these things mean? Do not expect an equation related to that. All right. We have, so for engines, efficiency And we have E is given by W hot minus Q hot, energy going in, minus how much is wasted over that, times 100% equals, in terms of temperature, T hot minus T cold over T hot, where again, both the temperatures are in degrees Kelvin. So this will be the efficiency, whatever units, as far as that. So basically, this is also W over Q hot times 100. So work done, basically the work done divided by how much energy you put in to do that. So that's engines and efficiency as far as that is concerned. We're not doing anything on refrigerators. And so that's section 15.5 or so. I'll leave that up. Okay. And the next section we'll be doing, the final section of this chapter is on 15.7 on entropy. We've talked about that, and the fact that delta S is Q over T, where this is the change in entropy. This will be in joules, and then this is in Kelvin. So delta S is in joules per degree Kelvin, or kilojoules per degree Kelvin. So we had entropy of phase change. All right, like ice to water, or it can be water to steam, and also entropy of mixing. All right, hot water, cold water, mix them together, and you have the change in entropy, which we talked about that already. So again, this will be entropy as far as that, and the fact that entropy of any system will always increase over time. And it's a little bit about statistics and such, about distribution. Talked a little bit about that as far as distribution. You know, we talk about entropy of a gas, all right? You have a gas all here, open it up, it will spread out. It's theoretically possible all the gas could go back to the same spot, but that is extremely unlikely. So that's chapter 15, okay? So I'll leave that there. All right, move on to the next section. Next chapter, I should say. And that would be chapter 16. And that is on electricity, electric field, and charge. And this also carries into chapter 17. We talk about electric potential. So chapter 16, so section 1 and 2, we talk about electrons and protons as the charge, right? Power charge is equal and opposite. 1.6 times 10 to the minus 19th coulombs. The unit of electricity is charge is the coulomb, and that's the charge of electron and proton, just opposite signs. We talked about insulators and conductors, and what's the difference? examples of both. We also have, we get into semiconductors. So that's section 16.3, just briefly what that is. All right. So that's all we have so far. 16.5 is Coulomb's law, and that's force is K Q1 Q2 over R squared. We're getting K is 9 times 10 to the 9th. And I'm not going to deal with the units. And force is in newtons. Charge is in coulombs. R is in meters. So that would be meters squared. So again, this compares with gravity of G M1, M2 over the distance between the charges squared. So force of electricity is this. Force of gravity is this expression which we had before. For this, we talked a little bit about how this is much stronger than that, but the fact that gravity is always attractive, but for the most part, electrical charges have a tendency to cancel each other out. So that's what we have there. We have some examples related to that. We're only going to be dealing with one dimension when we talk about charges. So you talk about force and charge is two charges, either plus or minus, a distance away, and we did some examples related to that. Okay, so we're only going to be talking about one dimension when we deal with that issue. Okay, let's see here. Might be about it. Yeah. So leave that. Again, that's K. And all right, the last section. (16, 7, and 8) are electric field. And for the most part here, I mean, technically, E is given by KQ over R. And what we're mostly looking at here are field and field lines. Okay, so we have a charge, say plus charge. What do we mean by electric field by that? What we do is put another charge here. Where would that charge, this one is fixed, where would that one move? And because they're both positive, it would repel in a circle like that. All right, so it'll go straight out. Then if we have a plus and minus, what does that mean? It does this sort of thing, much like a bar magnet. So we talked about those to some extent as far as electric fields and electric field lines. And that's the extent of pretty much what we did with chapter 16. And then finally, what we have, if we have a parallel plate, electric field is constant, right? So E is constant, but they go across. So plus charge here would go flying across to the negative charge there. Last section here we're going to do. The last chapter we're going to do is, for this first exam, is chapter 17 on electric potential, which is basically voltage, and that is relationship. An easy example are two parallel plates, plus minus. We have an electric field between them, and if the separation between here is D, then the voltage, so this is a constant electric field, so E is constant, and that's in units of volts per meter. Then V, which is in volts, or capital V, is E times D. So the voltage across here would be E times the voltage times the separation. So as an example, we talked about this before. So that's for parallel plates. So like that could be both sides of a battery. And then we talked about that if we put a charge in here, some charge Q, then the energy, potential energy, is Q times V, and that gets converted into kinetic energy of 1/2 mv squared, and we talked about that before. So Q times V is in units of joules. So a coulomb times a volt is a joule. We talked about that. We talked about point charge. So point charge, this is Q, and the potential a distance r away, V is KQ over R. Well, that's the distance away, K is the constant we had before, and Q is the charge on there. All right, and then, we talk about this again, relationship is, for the most part, because charges are pretty small, we defined 1 eV is the charge of 1 electron under 1 volt. So that's 1.6 times 10 to the minus 19th joules is 1 eV. So we talked about that as far as potential. Okay. I got a little, so that's the first part of the section, or chapter I should say. Move on to the last part here, next part. All right. Again, for capacitance, 1717, a capacitance all right, we use units of F, which is a farad. All right, so capacitance uses farads. Q uses coulombs, which are capital C. So, and then for two parallel plates, which have a charge on equal side and a voltage between them, then the relationship Q is C times V. So if that's charge on opposite charge on a parallel, like a battery, that's the voltage of the battery from one side to the other. That's how we define the capacitance, the relationship there. For parallel, I don't know if I'll get into more than that. So whatever other problems related to that. And we talked about energy. All right, so energy is P is 1/2 Q V squared, or 1/2 CV squared. I think that's correct. 1/2 QV, or 1/2 CV squared. So that's the energy. And that's really all there is to chapter 17. There isn't a whole lot to it. So that's the topics for the test, which will begin this week, early next week. And look at that. Email me questions. The chapter review quizzes will be open until the morning of the test. And good luck with that.